You know that feeling when you hit a patch of thick morning fog? It just feels so passive, almost stationary, like the world decided to just wrap itself in a big, damp cotton ball.
It does, doesn't it? But that image is, well, it's completely misleading.
And that's what we're getting into today. We're doing a deep dive into new research that shows fog is anything but passive. We're talking about surprising speeds and these invisible forces that can create and destroy it.
Exactly. We're looking at the quantitative studies. It turns out fog is governed by this really delicate high-energy balancing act, and our mission today is to understand how it can move faster than the wind and what determines whether it, lives or just evaporates.
Okay, let's start with the basics then.
Yeah.
We all know fog is just a tiny water droplets that reduce visibility to less than a kilometer, but it has some really strange effects, right? Like with sound?
Oh, absolutely. The classic foghorn is a perfect example.
Right. Why do those low-pitched sounds travel so much farther in fog?
It's because the fog itself creates a structure in the atmosphere. It often forms what's called a temperature inversion right near the surface.
An inversion, so warmer air sitting on top of cooler air.
Precisely. And that layer, it acts like an atmospheric duct. It actually dampens high-frequency sounds, but for low frequencies, it's like a channel. It helps them travel huge distances. It really shows you fog is structural, not just mist.
And that structure can be a huge benefit. I mean, it's a critical resource in some places.
A literal lifeline.
Yeah.
In nature, you see redwood forests getting, up to 40% of their moisture from fog drip.
And we've learned to copy that with fog nets in dry coastal areas to get drinking water. It's amazing.
It is. But let's get to the speed, because this is where it gets really counterintuitive.
Yeah.
Research on these huge fog events, like one studied over Jiangsu, China, saw something puzzling.
What was that?
Rapid propagation.
Mm-hmm.
Satellite data tracked the leading edge of this fog bank, and it was advancing at a maximum speed of around 9.6 meters per second.
Wait, hold on. That sounds incredibly fast for fog. What was the wind doing on the ground?
And that's the kicker. The ground wind was consistently measured at less than 3 meters per second.
So the fog was moving 3 times faster than the wind you'd actually feel standing there.
Exactly. So ground level meteorology, on its own, it just couldn't explain it.
Okay, so if the wind on the ground isn't pushing the fog, what is?
The primary driver is something called the boundary layer low-level jet, or BLLJ.
A low-level jet, so a fast-moving river of air.
A perfect way to put it, it's a high-speed zone of air, but it's close to the surface, somewhere between 50 and 500 meters up, and its core speed, around 10 meters per second. It perfectly matched the fog's speed and direction.
So it's not pushing the fog that's already there. It's carrying the ingredients for fog to form instantly, right ahead of the boundary.
You've got it. The BLLJ does a few critical things. First, it transports all this moist oceanic air inland, which helps condensation happen really fast. Second, it strengthens that temperature inversion we talked about.
Which traps the moisture.
Right. And third, and this part is just so elegant, it helps form low stratus clouds up high, and then the jet actually forces that cloud layer to sink and mix downwards, becoming fog on the ground.
So it's this active process of transport and conversion. That's one half of the puzzle.
Yeah.
What about its internal life, this battle between creation and destruction?
Well, the creator, especially at night, is long-wave radiative cooling. The top of the fog radiates heat powerfully up into the cold night sky.
Okay.
And that cooling process is the fog's engine. It's constantly producing more liquid water, sustaining and thickening the whole layer.
But then the sun comes up and everything changes.
That's right. Solar radiation, or shortwave radiation, is the great dissipator. The droplets absorb that energy, they heat up internally, and they evaporate. The ground also warms up and sends heat back into the fog, speeding it all up.
So for anyone trying to forecast this, what's the one thing that matters most for predicting when the fog will finally break?
The research is pretty clear on this. It's the presence of an overlying cloud layer. If a higher deck of clouds moves in, it acts like a blanket.
A blanket that traps the heat.
Well, more like it blocks the cooling. It cuts off that long-wave radiation engine we just talked about. Without its main source of liquid water production, the balance just tips decisively toward evaporation, and the fog vanishes.
Understanding that delicate balance is so key to modeling these complex systems.
It really is.
And, uncovering where these cutting-edge processes can make the most impact is crucial, whether in the atmosphere or in business. This deep dive is sponsored by Embersilk. If you're looking to uncover where AI agents could make the most impact for your business, Embersilk specializes in AI training, automation, and software development. You can find out more at embersilk.com.
And really, that's the hopeful part of all this. The detailed quantitative work on fog, this fast propagation, these radiative budgets, it's giving us a much deeper understanding of how all clouds form, even in what seem like very stable conditions.
So it points toward much better prediction models in the future.
I think so, yeah. It's incredibly optimistic. We're really on the verge of some exciting advancements.
And that focus on advancement and understanding is exactly what we love to explore. If you enjoyed this deep dive, please subscribe to the show.
Hey, and leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.